Mathematics, as in the study of quantity, structure, space, and change, has a long and storied history. The word itself comes from Greek, meaning knowledge, study, and learning. However, its roots lie deep in the Chinese, Indian, and ancient Near Eastern traditions. In the Mediterranean or Western tradition, the Babylonians, drawing on the Sumerian legacy, developed a base 60 counting system, which remained dominant throughout the Eastern Mediterranean until displaced by the Pythagorean decimal system. They were also the first to deal with squared numbers and quadratic equations, which is where an unknown number is multiplied by itself, for instance, x to the power of 2. This was obviously an outgrowth of the bureaucratic need to administer and divide plots of land in those intensely agricultural empires. The Babylonians also turned their mathematical skills to understanding and predicting astronomy, which was important not merely from a scientific angle, but also immensely important from a religious, oracular, and astrological perspective within that society. The Egyptians similarly contributed to early mathematics. Unlike the Babylonians, they developed a base 10 counting system based upon our 10 fingers. The Egyptians also developed a fully functioning arithmetic, including addition, subtraction, multiplication, and division, as well as some evidence that they developed fractions, prime numbers, and possibly quadratic equations. Mathematics in this sense was primarily concerned with practical issues, and the codification of Egyptian mathematical principles was primarily for the purpose of architecture and building. Egyptians recognized that a triangle with a ratio of sides being 3, 4, and 5 units in length would always return a right angle. Similarly, the Egyptians used practical solutions when faced with the issues of determining the area of a circle. They recognized that the area of said circle, if the diameter is taken to be 9 units, is similar to an area of a square with a side of 8 units. Therefore, an accurate approximation of the area of the circle was to multiply the diameter by 8 over 9 and then square it, giving an approximate value of pi accurate within less than 1%. Both the Egyptians and the Babylonians developed impressive mathematical systems. However, they were primarily concerned with the practical use of maths in architecture, engineering, taxation, and administration. It was the Greek world which would benefit from this rich mathematical tradition, which then generalized mathematics and took it to new heights. One of the first Greek mathematicians was also one of Greece's first recorded philosophers, Thales. It is reported that Thales travelled to Egypt, where he learnt mathematics and then went on to develop a very sophisticated mathematical understanding, which eventually allowed him to predict an eclipse. There is 2 theorems which are accredited to Thales, both demonstrating a further abstraction and generalization of mathematics, and in this case, geometry. The first discovery is called Thales' theorem. This states that if any triangle is drawn inside a circle using the diameter of the circle as the hypotenuse, or long side, it will form a right-angled triangle. This appears to recognize something fundamental about how the interrelation of geometric objects in space leads to natural harmony, and it is this focus on patterns and ratios which was key to all of Greek mathematics and geometry. The second observation is called Intercept Theorem, and is a little bit more complex to understand. However, at a more general level, it proves the natural harmony between geometric objects. Specifically, it demonstrates the ratio between line segments when 2 parallel lines are intercepted by 2 intersecting lines. Firstly, it observes that the ratio of segments on the first line equals the ratio of that according on the second line segments. Secondly, it states that the ratio of the 2 segments on the same line starting at the point intersection equals the ratio of segments on the parallels. Thirdly, the converse of the first statement is true as well. For example, if the 2 intersecting lines are intercepted by 2 arbitrary lines, and the ratio of segments on the first line equals the ratio of according segments on the second line, then the 2 intercepting lines are proved to be parallel. Finally, if you have more than 2 lines intersecting at a single point, then the ratio of the 2 segments of a parallel equals to the ratio of the according segments on any of the other parallels. Intercept theory can appear to be very abstract, but it has real benefits. It is stated that during his Egyptian adventures, Thales used the theorem to discover the height of the Great Pyramid of Giza. Firstly, he measured the height of a stick and the shadow that it cast in the sun. Secondly, he measured the shadow cast by the pyramid, factoring in half the width of its base so as to give the length of the pyramid's shadow as if it was acting like a pole. With this data, he was able to treat the pole of the pyramid as two parallel lines, intercepting the intersecting line formed by the shadow and the ground. Finally, he then used this data to be able to calculate the true height of the pyramid. Pythagoras, as has been previously explored in another video, lies somewhere between mathematician, philosopher, and religious figure. It is very difficult to separate out what Pythagoras himself developed and what was developed later in his followers and his own school. However, both the Pythagorean school and Pythagoras himself remain important figures within Greek mathematics. One of the most important and influential ideas developed by this school was the base 10 system of counting in Greece. Although the Greeks had previously experienced with the Egyptian base 10 and Babylonian base 60 systems, the Pythagoreans put forward the idea of the tetractys. The tetractys saw the number 10 as important, not on some anthropocentric level due to the number of fingers we possess, but rather because of the seemingly beautiful interaction of the sum of the first four numbers, 1 through 4, which equals 10. This idea became very influential in early Platonic cosmology. Perhaps the most famous Pythagorean discovery was what came to be known as the Pythagorean Theorem, that for any right-angled triangle, the square of the length of the hypotenuse, which is the longest side opposite from the right angle, is equal to the sum of the square of the other two sides, or legs. Generally, this is written as an equation, a squared plus b squared equals c squared. This was a generalization of the rope rule, which the Egyptians had previously developed based on the principles of 3, 4, and 5 units. This simple unit became known as the Pythagorean Triple, special because it used whole units. However, there is a theoretically infinite number of Pythagorean triples. 5, 12, and 13, 6, 8, and 10, 7, 24, and 25, 8, 15, and 17, 9, 40, and 41 are examples of this with such a unique composition of whole numbers, and are not just scaling up of a smaller Pythagorean triple, such as 6, 8, and 10, which is just a simple scaling up of 3, 4, and 5. Mathematics generally, and Pythagoreanism specifically, went on to have a tremendous impact upon the Platonic Academy. The tetractys was seen as the first creation emerging from the intermingling of the one and the dyad in Platonic cosmology. Furthermore, it is reported that the gates to Plato's academy was inscribed with the words, "Let no one ignorant of geometry enter here." However, the Platonic school also developed some novel ideas in geometry, in particular the development of the Platonic solids. These were the only 5 solids constructed from the same regular shapes on all sides. These were in turn associated with elements and were considered the fundamental building blocks of the universe, as discussed in the dialogue Timaeus. Anyone familiar with role-playing on tabletop games should recognize most of these solids as the common shape of dice, including the iconic D20. Besides these shapes, Platonists also delved into and contemplated classical impossible problems of ancient Greek geometry, often called the 3 classical problems. The first of these was called squaring the circle, which required the problem solver to construct a square with an area exactly equal to that of any given circle. The second was so-called doubling the cube, which required the construct of a duplicate of a cube with exactly twice the volume of any given cube. The third was called trisecting the angle, which required constructing an angle exactly 1/3 of any given angle. Although all 3 of these problems are actually impossible to solve using purely Euclidean mathematics, it wasn't until the 19th century that European mathematicians discovered this. Now that I've mentioned the name, it is time to discuss the most important of the Greek mathematicians, Euclid. Almost nothing is known about Euclid as an individual, but he probably studied for some time in the Platonic Academy and flourished in Alexandria, Egypt, where he served the Ptolemaic kingdom in the Great Library. Sometimes called the father of geometry, Euclid wrote a hugely influential text called the Elements, which survived in the West as the definitive geometry work right up until the 19th century. Although Euclid didn't necessarily invent anything new, he drew upon a rich legacy of his predecessors and laid out these discoveries in a logical and clear style. In all, the Elements contains 465 theorems and proofs, described in clear, logical, and elegant style, and requiring the reader only to use a compass and straight edge to demonstrate these proofs to themselves. Euclid developed 5 general axioms which seem to describe the way in which space and quantity worked around himself and can be seen even today in the way in which we experience generally flat spacetime. 1. Things which are equal to the same things are equal to each other. 2. If equals are added to equals, the wholes are equal. 3. If equals are subtracted from equals, the remainders are equal. 4. Things that coincide with one another are equal to each other. And 5. That the whole is greater than the part. From these axioms, Euclid was able to derive 5 geometrical postulates which describe the way in which shapes interact with each other in the real world, at least the real world as Euclid perceived it. 1. It is possible to draw a straight line from one point to any other point. 2. It is possible to extend a finite straight line continuously in a straight line. For example, a line segment can be extended past either of its endpoints to form an arbitrarily large line segment. 3. It is possible to create a circle with any center and any distance, for this case a radius. 4. All right angles are equal to one another. For example, half of a straight angle. And 5. If a straight line crossing 2 straight lines makes the interior angles on the same side less than 2 right angles, so as 2 lines cross a single line, they are bending in towards each other, if produced indefinitely, they will meet on that side on which the angles are less than the 2 right angles. Essentially, this means that if there are any 2 lines that are intersecting towards each other, if they are extended out an arbitrarily long distance, eventually they will intersect. Using these mathematical gems, the 13 volumes of the Elements contains formulas for calculating the volumes of solids such as cones, pyramids, and cylinders, proofs about geometric series, perfect numbers, and primes, algorithms for finding the greatest common divisor and least common multiple of 2 numbers, a proof and generalization of Pythagoras' theorem, and proof that there is an infinite number of Pythagorean triples. Besides these fundamental postulates, the Elements includes a series of theorems on the properties of numbers and integers, marking the first real beginnings of number theory. Euclid was the first to realize and prove that there is an infinite number of prime numbers. He identified perfect numbers, which are the sum of all their divisors, and was the first to define the golden ratio in terms of ratios, and to describe its presence in numerous geometrical shapes and patterns. After Euclid, the next most important, and probably the most famous, is the mathematician, scientist, and engineer Archimedes. Little of his life is known except that he came from the city of Syracuse in Sicily. He put his talents to work building war machines for the Syracusans and helped to keep the siege of Rome at bay. However, legend has it that when the Romans finally did conquer the city, it was ordered that such a brilliant mind should be spared. Unfortunately, the story goes that Archimedes was busy drawing diagrams of the dust when the Roman soldiers found him, and, angered when he refused to meet their demands and come and meet the Roman general, killed him on the spot. Supposedly, his final words were, "Do not disturb my circles," a reference to the diagrams he had been working on. Archimedes' most important mathematical advancement was the development of the method of exhaustion. This was a method to determine the area of the shape by using the area of shapes that he already understood. For example, to understand the area of a circle, he would enclose the circle in a triangle, then a square, pentagon, hexagon, and so on, each time approximating the area of the circle more closely. Archimedes' most sophisticated use of the method of exhaustion, which remained unsurpassed until the development of integral calculus in the 17th century, was his proof, known as the quadrature of the parabola, that the area of a parabolic segment is 4/3 that of a certain inscribed triangle. He dissected the area of the parabolic segment, the region enclosed by a parabola and a line, into infinitely many triangles whose areas form a geometric progression. He then computed the sum of the resulting geometric series and proved that this area of the parabolic segment was similar to that of the triangles. The most famous story regarding Archimedes is that which led to the creation of this so-called Archimedes Principle. A crown had been made for the king of Syracuse, who had supplied the raw gold for its construction. Fearing deceit by the goldsmith, the king asked Archimedes to determine whether the crown was wholly gold or whether it contained an admixture of silver. While musing over this problem, he took his daily bath, and Archimedes noticed that the level of water in the tub rose as he got in, and he had a sudden inspiration that he could use this effect to determine the volume, and therefore the density, of the crown. In his excitement, he apparently rushed out of the bath and ran naked through the streets, shouting, "Eureka! Eureka!" or "I've found it! I've found it!" This gave rise to what has become known as the Archimedes Principle. An object is immersed in fluid is buoyed up by the force equal to the weight of the fluid displaced by the object. The final great mathematical mind of the classical Mediterranean is a man called Diophantus. He lived in Alexandria, Egypt, and was either Greek, Egyptian, Jewish, or even potentially Babylonian in ancestry. He also made important advances in mathematical notation and was one of the first mathematicians to introduce symbolism into algebra, using an abridged notation for frequently occurring operations and an abbreviation for the unknown and for the powers of the unknown. Diophantus' most important work was a book called Arithmetica. In this book, Diophantus provides 130 algebraic problems. An example of such equations, called Diophantine Equations, is the proposition of two integers such that the sum of their square is a square, x squared plus y squared equals z squared. Examples being x equals 3 and y equals 4, giving z equals 5, or x equals 5, y equals 12, giving a z equals 13. Diophantus then demonstrates proofs for the equations giving either determinate solutions, where one solution exists, a theoretical infinite number of solutions, or proving that the problem is insoluble. He does this through a 5-step analysis, called Diophantine analysis, asking the following questions about the equation. 1. Is there any solutions? 2. Are there any solutions beyond some that are easily found by inspection? 3. Are there finite or infinite numbers of solutions? 4. Can all solutions be found in theory? And 5. Can one in practice compute a full list of solutions? Diophantus prefigured later Arabic and European developments in algebra, and it was not until the mid-20th century that his list of problems would finally be solved. The tools of classical mathematicians would continue to be developed throughout the Middle Ages, with applications in bureaucracy, architecture, and engineering. Islamic and Christian mathematics was built upon this basis, and it wasn't really until the Golden Islamic Age and the European Renaissance that mathematics began to progress beyond this basis. Some of the ideas and problems dreamt up by the classical mathematicians had to wait until the 19th and 20th century for solution. With this in mind, we should consider the enduring legacy of these thinkers, despite the advances made in mathematics in the following millennia.